and introducing us to their research there. Please, go ahead.
Thank you, and thank you for the organizers for inviting me here to this beautiful location. So today I'll be talking to you about our work of using laser-cooled molecules for a wide range of quantum science applications and fundamental physics. So let me first begin this talk with a very quick overview of why are we interested in ultracold molecules and what are their applications. Then I'll talk briefly about how we go about laser cooling these molecules, and then a bit more about the research we do with laser-cooled molecules and optical tweezer arrays. And then finally, I'll finish the talk with talking about some new research directions with new types of molecules. So what are the applications of ultracold molecules? Well, this can kind of be put down into basically these three general topics. They can be used for quantum simulation, quantum computation, which is, of course, why most of you are here today. But they additionally also have interest for studying ultracold collisions, ultracold chemistry, as well as for precision measurement applications. And let me just spend a few minutes really explaining to you why you'd want to use molecules for each of these applications. So why would we want to use molecules for quantum simulation and quantum computation? And this has to do with the fact that molecules have strong and tunable long-range interactions arising from the electric dipole-dipole interaction. This interaction is, of course, in the ground state of the molecule, so this also means that they actually have very long coherence times. They have a rich internal level structure, which means they can be very easily controlled and manipulated with a wide range of fields, ranging from optical fields, RF fields, microfields, and so on. And of course, just like atomic systems, these can, of course, be very easily scalable because all molecules are identical. And because of kind of all of these nice advantages, there's been a lot of theoretical work over the past several decades of using ultracold molecules for really a wide range of quantum simulations. And just a small subset of the kind of models that have been studied are listed here. Now, the same properties that make molecules good for quantum simulation also make them very useful for quantum computation. And people have looked into specifically using ultracold molecules in optical tweezer arrays, and they find with fairly reasonable experimental parameters, you should be able to reach on the order of about 4 nines of fidelity. Additionally, because of the rich internal level structure of molecules, one could also imagine using molecules not just as qubits, but also as qdits, as well as they've also been shown to have various opportunities for quantum error correction. Another kind of research direction we're interested in pursuing is, of course, also studying more the chemistry aspect and really studying ultracold collisions. And really just even understanding what happens when two simple molecules collide turns out to be filled with a bunch of very rich physics. And this involves basically long-lived intermediates, and with basically the full quantum control that we have with laser cooling, we can really have quantum state control over the reactants, as well as the readout of our products. Additionally, one can imagine studying, for example, the effects of external fields on these collisions. You can map out potential energy surfaces to benchmark quantum chemistry calculations. You can study, for example, the effects of entanglement in these reactions. And as we kind of build up the tools to laser cool larger and larger molecules, you'll see we'll begin to approach molecules that maybe are a bit more, or at least chemists might find a bit more used to what they're seeing. Finally, the last kind of broad arc of using ultracold molecules is to use them for precision measurements. And here, fundamentally, the reason we want to use molecules for precision measurements has to do with the fact that near degeneracies and the molecular structure itself leads molecules to have an enhanced sensitivity to external perturbations. And fundamentally, in any sort of precision measurement, that's what you want to have. You want to have the highest possible sensitivity to some sort of perturbation. And there's been a lot of work in this direction using these molecules for both studies of fundamental symmetry breaking, as well as variation of fundamental constants and other types of precision measurements. And all of these precision measurement applications could also be further enhanced in the future with, for example, applying spin squeezing to them. So how do we actually go about producing ultracold molecules? We do it with laser cooling. Now, of course, this presents a problem in the sense that, unlike atoms, when you excite them up to some excited state, molecules usually end up in a large range of various internal states after you do some sort of photon excitation. So we really need some way of controlling how these molecules will decay such that we don't need an infinite amount of lasers to repump all of the transitions that you would have in a molecule. So let's look at kind of the degrees of freedom that we have in the molecule. We have, of course, the rotational degrees of freedom. And thankfully here, the decays are governed by selection rules. And specifically, we can make use of selection rules that arise from parity to achieve closed photon cycling by simply photon cycling on an n equal 1 transition to the n equals 0 transitions. Here, n is the rotational quantum number. As far as vibrational states are concerned, unfortunately, there are no selection rules. And here, we're really relying on the fact that we select the right type of molecule. What do I mean by this? We're looking for a type of molecule that has a structure that looks like this, where the probability of decaying to higher lying vibrational levels becomes exponentially suppressed. It turns out there is a large class of molecules that actually follow this pattern, and it's molecules that look something like this, where you have metal attached to some ligand. And because of orbital hybridization in the bonding process, what you find is actually the electron wave function is actually pushed away from the molecular bond and really localized around the actual metal atom. And because of this essentially basically decouples the electronic excitations from that of the molecular excitations. And then you find a molecule that looks like this will have this structure. Now, of course, you might ask, well, if all of the laser cooling is done on the metal, can I not just replace this atom with some other atom? And yes, you can. And in fact, you can replace it with some other molecule, or maybe even some more complex molecule. And actually, it turns out that even the molecule that looks like this, because of this reason, turns out to be laser coolable. And you can see, for example, even the molecule here, all of the electron wave function is really localized still around the calcium atom. So how do we actually really go forward and produce these molecules? So a quick overview is shown here. We use several different types of cooling techniques, beginning with first buffer gas cooling, where we simply collisionally cool the molecules with cold helium gas. And then we apply laser slowing to them and load them into a magneto-optical trap. At that point, we can perform further subdoppler cooling and then finally load them into optical dipole traps. So all of these steps look, of course, very familiar to what you might have in an atom experiment. Of course, there are some differences when you try to apply these to molecules, but I won't talk about most of those differences today. Once we're able to optically trap these molecules, of course, one of the very promising platforms that you've heard all about today are these optical tweezer arrays. And really, because of the controllability and scalability of these systems, we're of course very interested in applying these to ultracold molecules. And as you've already heard, there's been a wide range of work that has been done with such a platform. So we can simply then project these small optical tweezer traps and then load these ultracold molecules into these optical tweezer arrays. And you can find histograms that look fairly reasonable, where we can load always either 1 or 0 molecules within these arrays. We can then do very similar things to what you heard about today, which we can rearrange these arrays into defect-free arrays. And we can also have, for example, site-resolved addressing, where we can address a single molecule, but for example, not the neighboring molecule, and so on. We can, of course, also have full coherent control over the internal quantum states of these molecules, with various combinations of optical pumping pulses and microwave transfer pulses. And you can see here, for example, a typical Rabi oscillations between two different quantum states within these tweezer arrays. One of the first things we did once we had these optical tweezer arrays was actually to use them to study ultracold collisions in cold chemistry. And just as a very quick kind of recap of what we were able to do, basically what we did was we took 2 of these optical tweezer arrays, we merged them together, and then we could study collisions in this way. Of course, because we have quantum state control of these molecules, we can put them basically in any internal quantum state and map out, for example, the collision rates in these various states. What you find is basically we always have a quite high rate of inelastic loss. So then we also spent some time exploring shielding ideas, basically trying to prevent the molecules from colliding inelastically. And then we did this with microwave shielding, where we were able to suppress this inelastic loss. But what I want to talk a bit more about today is to use molecules more as molecular qubits. So specifically, what do we need in order to have molecular qubits? We need, of course, single particle detection and addressing. And kind of the optical tweezer array platform naturally gives this to us. But we also need long coherence times. We need some way of entangling the molecules together. And you'll see that we'll need some way of suppressing further motional dephasing. So let me talk a bit more about each of these in a bit more detail. So how do we get long coherence times within optical tweezer traps? Well, one of the largest shifts you might have in your tweezer trap is, of course, the AC Stark shift, which is giving you your trapping potential. Now, the problem with this is if you have 2 qubit states, and these 2 qubit states have different AC Stark shifts, then any change in the intensity of the light will then change the frequency of your qubit transition, and this will cause dephasing. The same idea is true if these states are sensitive to either magnetic fields or electric fields. Any sort of lab magnetic field noise, electric field noise, will shift these states and again cause dephasing. So in order to get long coherence times, we basically need to find a way to suppress all of these various effects. And specifically, we can do this by tuning our tweezer light to something known as a magic angle condition, where we basically tune the derivative of the light shift to have a 0 derivative. And this means that we're then minimally sensitive to any sort of, for example, change in the intensity of the tweezer trap light. When we park on this feature here, what we find is quite long coherence times. So we get about 100 milliseconds Ramsey coherence times. With an extra spin echo pulse, we get about half second. And with higher order dynamical decoupling pulses, we can reach several seconds of coherence time. And maybe one point I'd like to make here is that this is the coherence time of the actual qubit states. These are not, for example, storage states. These are states that can actually interact with one another. Also, maybe quite interestingly, is that if you look at this decoherence rate as a function of temperature, you find that we basically are linearly sensitive to temperature. And this means, of course, that in the future, if we're able to further cool the molecules to lower temperatures, we should be able to further increase these coherence times. Nevertheless, the coherence times that we have here are already significantly longer than the predicted gate time, so in essence, this is already a useful qubit. So at this point, we can then move on to actually entangling 2 molecules. So what we can do is we can take 2 molecules, bring them in close to one another, a few microns apart, with these optical tweezer arrays, and then we can see dipolar oscillations between these 2 neighboring tweezer sites. And you can see that this follows your 1 over r cubed dependence, as you'd expect for a dipole-dipole interaction. What you also see, however, is that as we bring the molecules closer and closer together, you see that the rate of dephasing dramatically increases. Why is this the case? Well, this has to do with the fact that the molecules are not at absolute 0 temperature. They still have some finite temperatures within these tweezer traps. And these tweezer traps, while they're very small radially, in the axial directions, they're actually quite large. And as a result, this thermal motion, as the molecules move back and forth, will change the relative spacing between these molecules as a function of time, and this causes this dephasing. Nevertheless, we can already use the existing dipole-dipole interaction here to then entangle these 2 molecules, and we can do a parity check to benchmark the Bell state fidelity that we have. And we find that a Bell state fidelity of about 90% or so. So this is a very good starting point. And of course, this is made even better because we believe that most of this dephasing is simply due to this thermal motion. And I just want to bring up the point that this is kind of a new qubit platform. Of course, molecules are a very newcomer here. In a sense, laser cooling was only figured out a few years ago. So hopefully we'll make rapid progress over the coming years here. So, of course, the first thing we need to fix, in a sense, is the thermal motion. So how do we do that? And the basic idea to do that is to perform Raman sideband cooling. So the basic idea of Raman sideband cooling is you drive a Raman transition between basically one quanta of motion to one less quanta of motion, and then you apply an optical pumping pulse to bring you back into this upper manifold. And then you simply repeat this over and over until you reach the ground motional states of your trap. There are some complications when you're trying to apply this to a molecule. Namely, this optical pumping pulse doesn't always do what you think it should do. But thankfully, much of the theory on how this could be done for a molecule was worked out by Mike Tarbott's group. And we simply basically followed this theory proposal as we tried to do this. And it turns out that maybe one more thing I'd like to point out is the fact that we also have very high initial temperatures. And this means that we actually occupy many, many modes, both axially and radially, so we're actually quite outside of the Lamb-Dickey regime. So this means that the cooling actually is a bit more complicated, and we actually need to first start to cool higher order sidebands before we cool the final sidebands. So you can see here, this is the result. So this is the initial spectra before we apply cooling. So this is us driving the cooling sideband and the heating sideband. Once you perform Raman sideband cooling to the ground motional state, you find that the cooling sideband disappears because now you're in the ground state, while the heating sideband remains. And from this data, we can then extract that we have about a 54% ground state fraction, or we have an average occupation of about n bar of about 0.2 on both the axial and radial direction. So this, of course, looks very promising, and we're now working towards going back to generating our Bell states, and hopefully we'll find much higher fidelities there than previously. In the future, we'd also like to perform optimized pulse sequences to further improve the fidelities, as well as start exploring these molecules as qubits, and we also have some ideas on how we can further increase the gate times. Now, what if we want to think beyond diatomic molecules? And I think this plot here from this review paper is kind of a nice kind of explanation on why, as you add complexity in your system, you also add new possibilities. So this is various quantum simulation models that you can achieve as you add more and more complexity to your system, but the same holds also, for example, for studying collisions or beyond the standard model of physics. As we add more complexity, we also get new opportunities. So specifically, the molecule that we work with in these polyatomic molecules is the CaOH molecule. So this is a linear triatomic molecule. And now we have a few additional degrees of freedom from what we had before. So before we had vibrational modes. Now the vibrational modes are replaced by stretching modes. But we now also have a bending mode. Basically, the center atom can move out of plane. And then you can have some hybrid mode of the two working together. So these are all the decays we need to care about, down to about the 10⁻⁴ level. So we simply apply about a dozen lasers or so, and this allows us to then cycle about 15,000 photons. And this is enough to do all of the laser cooling and trapping that I showed earlier. And again, we were able to basically do the same thing we had done on the diatomic molecules, load them into a magneto-optical trap, perform sub-Doppler cooling down to microkelvin temperatures, and then load them into an optical dipole trap. Now, one thing that has really always plagued kind of the laser-cooled molecule community is the fact that these magneto-optical traps are quite hot and not very dense. And you can really see this in the transfer efficiency between our magneto-optical traps into our optical dipole traps, that this transfer efficiency is quite low. So we'd really like a way to increase the density here. So let's take a quick aside and focus on why are these magneto-optical traps so hot and fluffy to begin with. And this has to do with various subdoppler forces that are actually at work when we magneto-optically trap these. So these molecules, because of their inverted angular momentum structure, have both a dark state and a bright state, but the bright state is below the dark state when we're red detuned. And as a result, the molecules will motionally couple from the dark state into the bright state, ride down this potential hill, gaining energy, before they get excited up and this process repeats. So this is basically a Sisyphus-like heating effect. And this means that if you look at then your kind of your Mott forces, you'll have your Doppler cooling wings, but then you also have this Sisyphus-like heating effect in the center that basically is fighting this Doppler cooling. And you can see this also in the experimental data. As we ramp down the intensity of the trap, we decrease the Sisyphus heating, and you see the temperatures decrease and the trap size also decreases. So one way to fix this that has been proposed is the idea of a blue detuned magneto-optical trap. And the basic idea here is that rather than operating when we're red detuned with these Doppler cooling wings and the Sisyphus heating profile, we instead flip the system around and we rely on solely this Sisyphus cooling effect at the center of the trap to give us the highest possible density. The original idea of this blue detuned magneto-optical trap was first worked out again by the group of Mike Tarbert a few years ago. And actually, the demonstration of this blue detuned magneto-optical trap for molecules, or diatomic molecules, actually was shown in several experiments around the world last year. So we spent some time trying to apply this to the CaOH molecule. Of course, the first thing you'd try is to simply blue detune your Mott beams. But because this is a quite complex system, we decided to go through the trouble of actually having basically a full 3D Monte Carlo simulation to really kind of understand the dynamics of what was going on in this Mott. And in doing so, we actually discovered something very interesting, which is the fact that if we add a third frequency here, you can see that trapping forces are greatly increased over this 2-frequency magneto-optical trap. And when we then went to the experiment and tried to apply this, we also saw the same thing, that by adding this third frequency, we were able to dramatically shrink the size of the magneto-optical trap and increase the density by actually over a factor of 20 over this 2-frequency magneto-optical trap. So as a result, actually, even though this is a polyatomic molecule with only about a few thousand molecules here, this actually represents the densest molecular Mott of any Mott to date because of this kind of this new magneto-optical trapping force. So at this point, you're probably wondering, what is this third frequency? What's going on here? So let's look at this third frequency and what it actually does. So this third frequency is very closely detuned to this other frequency here. So if we now only focus on kind of the effects of these two frequencies, what you find is basically these two frequencies will create basically two moving lattices. One with a sigma plus polarization moving one way, and one with a sigma minus polarization moving the other way. And basically what happens is that the molecule will be cooled into the moving frame of this moving wave, and then shuttled to the center of the magneto-optical trap and then dropped off. So you can also see this in velocity as a function of time, that the molecules basically are cooled into this moving frame. They're shuttled at a constant, basically lattice velocity into the center of the trap and then dropped off. You can also see this in these animations here from this simulation, showing both as you're compressing the molecules to the center. If you look at the velocity, initially actually the velocity accelerates the molecules basically to this lattice velocity, and then once they're in the center of the trap, then drops them off. So we actually believe that this is kind of a new mechanism for magneto-optical traps, which we're calling the conveyor belt Mott. And we think that this could actually be applicable not just to these molecules, but also possibly to other atoms. So now that we have more molecules loaded into these optical dipole traps, we've also looked at a few other things. So we've characterized, for example, all of the various lifetimes we have of these traps in various bending modes and internal states. We've regained kind of the quantum control that we had for the diatomic molecules, but in these polyatomic molecules. And now that we have this greatly increased density, we can also start studying collisions between these polyatomic molecules, as well as we're trying to now shield, again, these collisions against inelastic loss. In the final 5 minutes or so here, what I'd like to talk about is two various research directions that we've gone down. The first is a precision measurement route, and the other is loading them into tweezer arrays. So on the precision measurement side, one of the main applications of ultracold molecules is to search for the electron-electric dipole moment. As a very brief review, the standard model has an electric dipole moment, but it's at a very, very low level. And the level is too low to explain much of, for example, the astrophysical observations that we have today. There are various beyond the standard model theories that predict a greatly increased size of the electron dipole moment, and currently the best search for the electron dipole moment comes about from these molecular beam or molecular ion experiments. And the basic idea of an electron EDM search is the fact that you're using the fact that an electron within a molecule sees a very high electric field, and you're basically looking for a shift in the energy depending on the orientation of your electron. Now this, basically the sensitivity you have is proportional to the internal electric field strength, and because this is a relativistic effect, you actually need to pick a very heavy molecule to get this very high gigavolt per centimeter field. And because of this because of this very high field, some of the most stringent limits to CP violation actually come about from these molecular electron EDM searches. And for several reasons, including laser coolability, we'd of course like to use ultracold polyatomic molecules to improve on the current limitations. So we basically started a new experiment, which was kind of an electron pathfinder experiment, where we basically prove the techniques of performing electron EDM search on these polyatomic molecules. So this basically involves loading them into an EDM state and performing then sprint procession here. One thing that was interesting that we spent some time on is the fact that because this is a polyatomic molecule, you can actually use the additional degrees of freedom you have to tune the magnetic field sensitivity with an external electric field. And what you can find is you can actually tune the magnetic field sensitivity to a zero crossing. So this is, of course, very nice in the precision measurement because that means you can get enhanced coherence times by suppressing the effect of, for example, ambient magnetic field noise within your lab. The last kind of research direction I want to talk about is, can we now load these polyatomic molecules into optical tweezer arrays? So of course, we've already showed that we can do this for diatomic molecules. Is there some new limitation when we try to put polyatomic molecules in optical tweezer arrays? And initially, when we started doing this, our histograms looked something like this, and it was basically very clear something was going wrong. This is very much not resolved of whether you have 1 or 0 molecules within your tweezer array. So what's happening? So earlier I showed you this picture of all the lasers we're applying. What I did not show you are all of these additional states that are up here. And what happens when we then turn on this tweezer trapping light is we're basically coupling all of these excited states to all of these other excited states within this molecular structure. And this turns out to be quite complicated with many, many lines moving everything everywhere. So we spent some time actually mapping out basically the actual Stark shift of each of these various excited states as a result of this tweezer excitation light. So some of these we could predict ahead of time based on known spectroscopy of high-lying states. But at the same time, we also found other states that would move around due to states that were, for example, never mapped out or never seen before. But once we kind of understood this, we could then basically avoid all of these resonances and pick a tweezer wavelength that is kind of in a safe region away from these resonances. And when we do that, we can then load these optical tweezer arrays and again recover kind of the same histograms we had earlier, where it's very clear we now always load either 0 or 1 molecule. Additionally, we've then also been able to regain the single quantum state control and manipulation within these tweezer arrays. So hopefully we'll be able to pursue some interesting physics here. So that wraps up my talk. Hopefully I've convinced you that ultracold molecules are very useful for work for quantum simulation, quantum information, as well as for fundamental physics and ultracold chemistry and collisions. And with that, I'd like to acknowledge all of the many students that worked on this experiment, and thank you for your attention.
Loïc, thank you very much for a very interesting talk with lots of new directions. The talk is open for questions. Shoot, who wants to? Go ahead.
So,
I have to throw now that is dangerous.
Given the difficulties with CaOH, with the tweezers, with all the shifts, what is the perspective of going to even bigger molecules? Would you ever want to put an even bigger thing in a tweezer?
Yeah, that's a good question. I think the answer actually is that it's directly related to however many lasers you need to do the laser cooling. In a sense, each one of these repump lasers adds kind of a new pitfall of things that could fail. So even if you have a very complicated molecule, it's very likely that if you can find a very complicated molecule that doesn't need too many of these repump lasers, it should not be a problem to load them into tweezers. Even if the density of states up here goes up dramatically, you will still be able to find gaps, for example, between different electronic transitions where it shouldn't be a problem. Yeah.
Okay, thank you.
Yeah.
Thank you. So could you maybe say something further about these ideas to be able to increase the interaction rates between these molecules in the tweezers and ideas related to that?
Yeah, so of course the first thing is that, so right now we purposely have the molecules further away, and that's just because we had this motional dephasing issue. So now that that has been solved, we should be able to bring them much closer together. Additionally, there's other ideas here. So for example, you can make use of basically the tensor stalk shifts within your tweezer traps to actually load two molecules within a single tweezer trap and actually control the distances down to the nanometer scale level. So that's one idea that also was worked out by Mike Tarbott's group. And then there's also other ideas. For example, you could also use hybrid systems, combine Rydbergs with molecules, or you could imagine also loading them into sub-wavelength, other types of sub-wavelength lattices.
Thanks.
One more question? I don't see a hand, so thanks again, Loïc.